Well, welcome to Chapter 5 of Computational Optical Imaging, which deals with wave field imaging. So we've been through how to build forward model, how to invert forward models, and we've analyzed several different geometrical optical imaging systems. Today we refer back to the very first episode of this series where we talked about the challenge of imaging, where we have a object distribution f of x, y, z that is transformed into a measurement distribution g of x prime, y prime, and we want to estimate the object from the measurements. Today we introduce a third element, which is the field in the volume. And when we have wave fields, we can think of the field as something that has a value at every point in the volume that we could measure and then use to estimate the object. The challenge with the field then is going to be to figure out how do we transform the field from its measured on one value, one plane or one point in space to another point in space. With the field, we actually don't need optics. Once we've measured the field, we could calculate the field throughout the volume, and of course, then we'll have to think about what's the relationship between the field and the object itself. Here's an example of field propagation or diffraction. So this uses what's called the scalable angular spectrum method. It takes the field at one plane and propagates it to another plane. So any place in the volume, you could calculate the field. In this case, this is illustrating a sampling issue with this, that there's a ratio between the sampling pitch and the wavelength of the field that may determine how accurately you can estimate the field in the volume. And the image on the right is vignetted because the scale of the diffraction and the sampling pitch have some mismatch. So for that, I refer you to the paper cited here to understand some of the details. Of course, objects are not two-dimensional. Objects are three-dimensional, as we've seen throughout the course. And so this idea of propagating the field from a plane to a plane may not accurately reflect analysis of what happens to the field around three-dimensional objects. For that, you need more advanced numerical techniques, such as the finite element analysis, where you break the volume into cells and propagate the field through those cells. And here's an example of simulation of a optical element with a very, very simple interface using a finite element, which can be computationally very intensive and challenging. So let's get started in understanding how these processes work. Computational imaging. Episode 27, Diffraction. Okay, so we've been interested in the relationship between distributions at an input plane, which we've thought of as where the object might be in an imaging system, where we'd have distribution f of x, y, and an output plane where we'd make some measurements, in this case, g of x prime, y prime. So far, those have been relationships between object distributions and measurement distributions, but once we begin talking about wave fields, we can talk about the state of the radiation field everywhere in the volume at points in between the objects. One of the classic problems here, of course, would be given the radiation field corresponding to the object at the input plane x, y, could we calculate the radiation field at the plane x prime, y prime? And of course, once we know how to do that, we could propagate from the x prime, y prime plane back to the xy plane. And then we ultimately would have to think about what's the relationship between the object and the field. But we begin by talking about, can we propagate the field between planes, which is a process that we call diffraction. The field, as it propagates, satisfies the Maxwell equations and is described by a wave equation. One of the classic solutions to the wave equation, of course, is the plane wave. So a plane wave is a harmonic distribution, and here we have a f of x, y on the input plane would be this harmonic distribution with coefficients in x and y. This is an example of a plane wave that is propagating in the xz plane. What we mean by that is here would be the y-axis, the x-axis, and the z-axis. And the k vector here, the u is some non-zero value. V here is 0 because the constant wave fronts have no variation along the y-axis, which would be this axis here, and here's z. So u has some non-zero value, which would be along the x-axis. So this would be u would be here along the x-axis, and then there's some z component of the plane wave, which in this case would be square root of 1 over lambda squared minus u squared. And so that would be what we call u sub z, let's call it. And so the plane wave remains a plane wave as it propagates, and we see the same wavefront distribution in the diffracted wave a distance d away, but it has some phase shift as it's diffracted. Here's an alternative, of course, if the plane wave had no coefficient in the, if u was equal to 0, so now the wave has a non-zero k vector in the y direction. Here's z and here's x. So this would be a plane wave propagating up in this perspective, but it would remain a plane wave, and we'd see a phase delayed version of the plane wave at distance d away. Here's a plane wave that would be propagating, with a wave vector that would be somewhere having coefficients both in the x and y directions. Here's z, and this wave vector would be up in this direction and would remain a plane wave as it propagates. The plane wave over the space is defined by this form, so it keeps a harmonic coefficient, but now has this z coefficient that satisfies, in order to satisfy the wave equation, the magnitude of the wave vector k has to be equal to 2 pi over lambda, which means that the diffracted field has the same harmonic function in the x and y direction as the input field, but it's delayed by this amount, where we have this z component of the wave vector implementing a phase delay. So plane waves are modes of the wave equation, and as they propagate, they just are phase delayed in proportion to the distance that they propagate and the z component of the wave vector. Okay, so the plane waves are a complete description of the field, that we could break the field into a superposition of plane waves on the input plane, which we do with the Fourier transform, of course. So the Fourier transform of the input field is shown here, as we've seen them in our definition of the Fourier transform. And what we have just shown is that each Fourier coefficient of the input field is phase delayed by this amount, which would be the phase delay associated with a plane wave with x and y coefficients u and v. So now all we have to do to propagate the field from this input plane to the output plane is take its Fourier transform, multiply by this phase delay, and then inverse Fourier transform, and now we have a relationship between the input and the output plane waves. Now, this is called a transfer function, right? Anytime we have we multiplied the Fourier transform by a filter, that filter is called the transfer function. So this phase delay is the transfer function for propagation of signals in free space. Associated with the transfer function, we have an impulse response of the system. So the impulse response is the inverse Fourier transform of the transfer function. It turns out to have this form. For what we now dealing with here is a scalar diffraction. This basically is a spherical wave, as we call it, and the amplitude of the spherical wave goes as 1 over the distance propagated, so that would be d over this d squared, roughly speaking. And then this is a near field term for this particular transfer function. So if we had a impulse in the input plane, then the field distribution we would see on the output plane would be this impulse response. So using this method of implementing a phase delay with this transfer function on the input signal, we can calculate the diffractive field for any input wave. And that's done in the notebook that's available on the GitHub site that's associated with these lectures. So this implements numerical diffraction between two planes. This method of multiplying the Fourier transform of the input signal by a phase delay is called the angular spectrum method. So the angle here is associated with u and v have each corresponds to an angle of propagation of a plane wave, and so that's a spectral coefficient, and we multiply by the phase delay for that spectral coefficient to get the phase delay and inverse Fourier transform to recover the original field. A lot of times these systems are parameterized in terms of the ratio between the wavelength and the sampling pitch, which is done in this code. If the features are, if the sampling pitch is much smaller than the wavelength, these systems can become computationally challenging. So we're assuming effectively that the input field is smooth on the scale of this sampling pitch, because of course we have to sample at the Nyquist rate in order to accurately reconstruct the field. So there are limitations in how well these systems work, and you would need to move to, like, for example, a finite element analysis to model fields on a much finer scale than is done here. For example, metamaterials will use a much finer sampling period and may need a more sophisticated modeling strategy. But for fields that are associated with propagating waves that we would use in imaging systems, these methods work quite effectively. So the code implements this as shown here. There's a padding added, so once you've determined what the ratio between the sampling pitch and the wavelength is, then you would input here, and then you have an input field that we assume is sampled, of course, at the sampling pitch, and we're going to propagate it at distance d, where in this system the d is in wavelengths. So the signals that we're going to see are plotted in units of wavelength. So we pad the input field because in the normal course of events, waves that diffract will blur, which means that the size of the wave, the region of which we need to measure the wave, increases with diffraction. So we take the, we build a padded function to represent the wave, and we take the center of that function and put our input wave. Then we take the Fourier transform of the input field, multiply it by this transfer function, and inverse Fourier transform, and we've got the diffracted wave. Here's an example of this. So this is this wave that's now modulated by a cosinusoidal function. So cosinusoidal function means that it actually has e to the I ux plus e to the minus I ux. That's a cosine consists of these two harmonics. So if we take here a Gaussian field distribution, so the field has this Gaussian envelope, and we multiply it by a cosine, it has these two plane wave components. So as it diffracts, those two plane wave components separate into these two independent Gaussians that you see here. Now notice that the input field is only a couple hundred wavelengths across. The diffracted field here, we've diffracted it 10,000 wavelengths. So if the wavelength was 1 micron, we've diffracted it 1 centimeter, and it's separated into these two spots. But now we've got the size of the diffracted field is 3,000 wavelengths instead of 1,000 wavelengths that we had for the input distribution. And if we kept diffracting, of course, those spots are going to move further and further apart, with the angle determined by the frequency of the cosine that's modulating the fields at the input. Here's another example. So this field is a difference of two cosines, so it's a donut field where we have a broad cosine, or a broad Gaussian and a narrow Gaussian. We take the difference of the two Gaussians, and we see this donut, and it's modulated by a cosine soidal function. So as it propagates, those fields separate into two spots again. Interestingly, the donut fills in with diffraction, so we get a bright spot at the center of the diffracted field as it propagates. And here we've propagated it 10,000 wavelengths, which would correspond to a centimeter if we had one micron wavelength. Now, as the field increases, one of the challenges of the angular spectrum method is that the size of the Fourier transform, or the size of the input field, has to be equal to the size of the diffracted field. We're going to take the Fourier transform of a field distribution that's the size of the whole diffracted region. So as the field size, diffracted field increases, the size of the Fourier transform that would be required becomes large. Now, of course, these methods rely intimately on the fast Fourier transform algorithm, which makes it possible to take, for example, here a field that is several thousand samples on a side and take its Fourier transform. One method to deal with this would be to resample the field as it propagates. So here we have an input field that has several harmonics modulating some distributions, and we've sampled it at the range of about 1,000 wavelengths on a side, but sampled at about one sample for every 3 wavelengths. We propagated 5,000 meters, and you see the field begin to separate into spots. We propagated 25,000 wavelengths, and it's separated into 4 spots. 75,000 wavelengths, those spots have increased, but now we're up to 10,000 wavelengths on a side. This particular method was done with a multi-stage diffraction. So here's the code that implemented that. We've propagated the field to 5,000 wavelengths. That's what's shown here at the upper right. Now we want to propagate the field further to 25,000 wavelengths. There's no reason for us to start back at the original field when we want to propagate further. We can take the field at 5,000 wavelengths as an input, which is done here. So we have d equals 20,000 wavelengths. Now we're going to decrease the sampling by 2. So we've sampled at a certain rate relative to the wavelength. We're decreasing the sampling by 2. What allows us to do that is that we've resampled the field at 5,000 wavelengths. So the code line above what's shown here took the field at 5,000 wavelengths and rescaled both its real part and its imaginary part by a factor of 2 to downsample it to reflect this new sampling period that we have at this plane, and then we propagate that 20,000 meters and we get the field at 25,000 meters. Then when we want to go to 75,000 wavelengths, we take the field at 25,000 wavelengths and propagate it another 50,000 wavelengths, but we resample the field before we do that, and again, the resampling rate here is a factor of 2. This is allowed because we're assuming that the field is blurring, that it's getting smoother as it propagates. Now, technically speaking, the bandwidth or the spatial frequencies involved in the field are constant as the field propagates through space. But for the right kinds of field distributions, the field, as looked at in a plane, can appear smoother, and so that within a given plane, we can decrease the sampling rate and still accurately reflect the field. And this allows us to use fewer samples and allows us to propagate further. This is just one method for enabling diffraction to extend over larger and larger distances. The scalable angular spectrum method and a variety of other methods have been developed to deal with this problem. This course is not, of course, a course that's in the details of field modeling, but hopefully introduces you to the basic methods that you use to solve these diffraction problems, which, as you see here, can be very, very simple. All we do is take the Fourier transform, multiply by a transfer function, and inverse Fourier transform. You should be cautioned with this multi-scale method, of course, because fields do not necessarily blur when they propagate. They can focus. So here's an example of a chirped field, like what we're going to see very shortly as we talk about lenses, that with this particular phase modulation, as you propagate it, starts with the field on the left that's 3,000 wavelengths across, and as we propagate it 10,000 wavelengths, focuses to a spot that's just a few wavelengths across. So this is a focusing field. So fields do not necessarily blur as they propagate. They can also focus, and we can take fields and conjugate them in a plane and propagate them back in the reverse direction and use the same methods to propagate fields that are focusing and defocusing. And we'll use this now to figure out how to form imaging systems. But before that, we need to talk about how do we measure the field itself, which is a process we're going to use of holography. This, of course, is a famous hologram, but it's not actually a hologram at all. A hologram is an interferogram of fields. Can be used, as in this case, to display information, but for purposes of this course, we're mostly going to be interested in holography as a method to form images, computationally calculate the field and calculate the objects throughout a volume. And we'll talk about that in our next episode.